This midterm review brought to you by Lego Minecraft person with a tool or something. So your midterm is coming up, and I'm going to share with you kind of what I see as an overview of the content we've covered in each section for units 1 and 2. So we'll begin with unit 1.1, and one of the main things you need from here that I assume everyone at this point is feeling pretty confident about is converting a percent into a decimal. For example, if I give you 1,100%, to convert that into a decimal, you could take 1,100, divide by 100, and you get 1.1. That's the decimal version of 1,100%. Who said that? No, it's 11%, right? Or 11 as a decimal. 11.0 is 1,100%. The other problems you faced in here are a set of solving percent problems. And there were two main types. The first one was just calculating a percent of something. And here you simply multiplied by the decimal equivalent of that percent. And the second type of problem was find the original amount. And we could give you, given the discounted price, so we'll say given a new price, and that price could be given to you as, we could give you the percent discount or increase, that discount slash increase, or we could give you the percent of the original that remains. And the one that you need is this one to do the calculation, and you divide by that percent to figure it out. It's often taught, these types of problems are taught like percent times amount equals new value. So percent of an amount equals a new value. So if we give you the new value and you know the percent, where this is the original percent, not the percent remains. Boy, I can't spell remaining. Whatever, pretend like I spelled remaining there. Then you just multiply that remaining percent times the amount equals new. Think exponential decay and exponential growth kind of idea. That's the factor you're multiplying by. And then the last thing we encountered in unit 1.1 was this notion of percent increase slash decrease. How do we calculate that? And we gave you a formula. It was new minus old divided by old. This gives you the decimal version of it. When you multiplied times 100, you got the percent increase or decrease. If it's a positive number, it's an increase. If it's a negative number, it's a decrease. So then section 1.2, we really covered this heavily in project 1. Here you created a pie graph, and you needed to know that a sector, or the total amount of degrees in a pie graph was 360 degrees. And then you had to figure out sectors, so degrees in a sector, or we could say amount from in the sector. So if we told you, hey, this pie graph represents 5,000 items, and this particular sector is 17%, well, how many items are in that sector, that kind of idea. And then 1.3 was kind of a parallel section, because in here we talked about bar graphs, which are similar to pie graphs, except that bar graphs have to add up to 100%, whereas, pie graphs ended up have to account for 100% of the data, where bar graphs could have overlapping categories. So if you think about the problem that you looked at in this section, where we looked at the internet reach, so the amount of people that go onto Facebook each day versus the amount of people that go onto Google and etc. And many people go to both, and that would be counted for in the bars. And like the pie graph, we need to estimate values. when we give you a bad graph. So estimate values of bars, whereas for here you'd be estimating values of um, sectors, and then calculating percent of total for a bar graph, like how many are in this bar if it's a percent. 1.4, not a whole lot in here that I'm going to directly test. Here is where you were like taught how to estimate values from bad graphs, and to look at things in look at numbers in terms of position on a number line. We also threw at you the inequality notation like this, and you encountered the square root symbol. But we haven't really used this at all, and we really won't use that much more later in this class either. So I'm not a whole lot of questions here on the exam, probably none, to be honest with you. And then section 1.5, we did scaling. And this is really what you're doing in project 2 with your recipe. The idea here is how do you go from big to small and or small to big using your scale factors. And these could be given to you either as a ratio or a percent, either way, and you need to know how to work with that. And then the second thing in here is dimensional analysis, and this shows up again in chapter 2, converting unit rates into different types of measurements. So you need to understand what is a conversion factor, maybe write a couple, and how do you convert between units, which is precisely what dimensional analysis means. So canceling, turning miles into kilometers or inches into meters or whatever, that kind of idea. Okay, and now I'm on to a new page. We're hitting up 1.6. In 1.6, we talked about relative change. So we redefined the percent increase and decrease as relative change, and it's the same formula, new minus old divided by old. That gives us the decimal version of the relative change, and then we multiply it by 100. Recall we also use this in chapter 2 as to help us find the growth rate used with the growth factor. So you're going to need to, I could have mentioned this earlier, but in any case, when you calculate a number using this formula, you need to interpret your results in context. And essentially what you're going to tell me here is, what are we talking about? If necessary, when did this occur? And it's most always going to be necessary because we have this concept of a new value relative to an old value. So over what time frame did this happen? And then the how much. Positive, negative, so is it an increase or a decrease, and by what percent? The other thing we encountered in this chapter that you're expected to know, and also shows up on project 2, is relative error. And this one we kind of gave a new formula because there's not a change in time that we're talking about. There's a comparison between a predicted or an estimated value versus an actual value. And just like all the others, that's a decimal. When you do that formula, multiplying by 100 gets you a percent. If you end up taking 133 at Jackson College, you will see this formula or version of this written as a predicted value minus an observed value or a data value. And we call this top thing the residual, the actual difference. And then this is the relative difference. This is times 100. You'll be using this in project 2 when you make a prediction. So this is when you use the model. And then this is the collected data value. So it's the actual value that exists out there. And you can see how far off was your model, your linear or exponential model. 1.7, not a ton in there. There's really only one thing that we expect you to understand, and that's scientific notation. I am not going to ask you, I feel like I spelled that wrong. No, that was right. Scientific notation. I am not going to ask you to convert numbers into or to or from scientific notation. Well, I might. Mostly what I'm going to do is what you see in the unit reviews. I'm going to give you numbers in scientific notation and ask you to do calculations with them, or I'm going to give you numbers that when you use your calculator, that calculator will spit out scientific notation. So you've got to understand what that representation looks like and what that tells you. Just remember the A value, the number here is a number between 1 and 10, and the exponents are in the integer, negative, 0, positive values. 1.8 was a big section, the apportionment section. So what I'm looking for from you here on the midterm is not the mechanics so much. That's what you did in the project using Excel that automated all that. Hopefully that went well for you all. I'm more interested in, do you know the definition of apportionment? Like, what is it? And then when do we use it? And so along with that, I may test, do you still know the process? So like, can you talk to me about what the standard divisor means? Do you know what the standard quota is? What does it tell you? Why do you find it? What's up with that? And then how are the lower quotas and upper quotas used? Again, I'm mostly for these questions, my plan when I write the midterm is to ask you conceptual questions where you write a sentence. I know it's probably, you'd probably rather do the calculation. But if you have the definitions down and you have the formulas and you know what these things mean, in my mind, you should be able to demonstrate that you understand what they tell you. For example, the standard divisor, its formula is total population divided by the number of seats you have to give away. So this is the number of people or the number of things per one item you're trying to apportion. And this is kind of the beginning process of fairly distributing indivisible items. Okay, so I would put on your reference sheet when you're writing it any of these formulas and kind of a definition of what they mean, and then having an idea of how are these methods used. So there was Hamilton's method that we covered in the YouTube videos and in the textbook, and then Webster's, and I don't know if I'm getting these in the right order, and Jefferson's. And then if you did the extra stuff, there was Huntington Hill. I'm not going to require knowledge of Huntington Hill at all, but I'm just putting this on here so you know that that's talked about in the textbook, not required. And then none of these four are what we actually use, what Congress uses currently. I'd have to look it up again. It's a little more complicated formula to apportion the current seats in the House. So this is Unit 1. Let's jump to Unit 2. Unit 2, I think, has less content, but it's a little bit more complicated maybe. So what I suggest you do is fold your sheet in half, because there's really only two major concepts in this section, or in this unit. And that is everything linear versus everything exponential. And then there's one other little thing in Unit 2 is the average rate of change. So let's just fill out the linear stuff. So all of this is kind of spread out throughout the different sections. I'll tell you, when we talk about unit rates, that's section 2.2. So in general, we know that linear sequences or linear patterns are when we have addition of a constant. So we're adding the same value each time. Know that that constant could be positive or negative. So you could think of that as subtraction. Just remember that subtraction is addition. And then for exponential, it's multiplication of a constant. Now, this addition of a constant, this constant we called the slope. And when we had a set of data, set of ordered pairs, and over here, this constant is found using, it's related to the relative change. So I'll just put here relative change. It is not the relative change itself. It's 1 plus the relative change. Okay, so I'll just mention that there. And then when we get our set of data, a set of ordered pairs, the equation that we use to model that data is y equals mx plus b, where m is that number for the slope, and b is the y coordinate of the y-intercept. For exponential, the equation is y equals ab to the x. I should say that these letters, m and b and a and b, these are just chosen numbers. They're chosen letters. They could be anything we wanted. And here in the exponential, oh boy, did I write that wrong. The 0, a is the y-intercept. So this is the equivalent, the exponential equivalent of the linear y-intercept. And this b has the same function as the slope. It's the constant. And this is called the growth or decay factor. Depends on what version it is. So in your project and in Alex and other places, you'll see the word parameters. Those are the coefficients in these cases. So for the linear equation, the two parameters you have to find numbers for are m and b. And for the exponential, the two parameters are a and b. Just that's how we labeled it. So let's define those. We already did. B here is the y-intercept. The slope, we can, if we know points on a line or want to, we can calculate the slope. And that looks like this. It's the change in the x values divided into the change in the y values, and we called this the average rate of change. Because most often when we perform this division, we got a decimal, meaning we made the denominator 1, which when we say average rate of change, we could also use the word, this is a unit rate. For exponential, it's far more complicated. So if our growth factor is, or if our b is greater than 1, then we're looking at a growth function. And we might be told that it grows by a certain percentage. So I'll put over here as a little aside that R is the percent growth or decay that's often spoken about in a problem. And when we use it, it's always as a decimal. Okay, we never write it as the percent in percent form. And we find the b, if we're given that R, we find the b by doing 1 plus R. That's your growth. For decay, that occurs when b values are between 0 and 1. We call that decay. And this is found by doing b is equal to 1 minus the decay rate. So here R is called the growth rate or percent growth, and down here R is called the decay rate or the percent decay. Okay. And then with both of these, the y-intercept, as I've already stated several times now, right, is 0, b, but we often call this in the word problems the initial value, the time 0 value. So it's 0, b for the linear function, and for the exponential, it is 0, a. That's our y-intercept, also known as the initial value. Another important thing is to know what the basic shapes of the graphs are. So there are actually 4 basic shapes for linear models, but there's only 2 that we're really concerned with, and that is a growth equation, which has a positive slope. It would look something like this. That's for m greater than 0, or a negative slope, which could look something like this. Anywhere in the, anywhere on the x-axis, it could have any y-intercept. For exponential, there are 2 basic ones that we're concerned with, both of them with positive a values. When a is negative, we get different looking things. And so for growth, for exponential, we have this increase as x gets larger and larger and larger. So that's a b greater than 1. And then for the decay function, we have a value approaching 0. It never actually gets to 0 using our exponential model, but it gets really close. So we call this graph decay, we call this graph growth, We could call these over here, these linear graphs, growth and decay if we wanted to. We don't often use that language here. We often just say an increasing or decreasing line. All right, and then the last thing is making sure you know how to find these in Desmos. So for the linear function, it's this y, and then you put in the number that corresponds to the table in Desmos, and then tilde mx, the number plus b, where your data value looks like this. The default is 1. But if you have multiple tables, then you'll have a 1 and a 2 and a 3, and you can also change these. So you could label your table as H and K if you wanted to, and then you do H tilde mx or mk plus b. And Desmos spits out your parameters for here, the numbers for the parameters, and it also gives you the correlation coefficient, R. This correlation coefficient, capital R or lowercase r, I think Desmos does lowercase r, you interpret it by looking at a value, R close to 1 is a strong positive correlation, meaning that's a good fit for the model, and R close to -1 is strong negative, also a good fit for our model. So this would have negative R's, this would have positive R's. You may note in the Unit 2 Review B, one of the questions has the wrong R value. If you can point that out to me, maybe I'll give you some extra credit. Or no, not extra credit, we don't do that. Some redemption points. Over here for exponential, Desmos, you use y, the number, tilde, a, b, x to the number. And again, those numbers correspond to whatever the numbers are in your table. And same thing here, the correlation coefficient is R, and the closer to 1 means a strong fit, strong positive fit. Now, R is going to be close to 1 for both growth and decay. And then the other thing you need to do here is make sure you select the log mode button to get R. The reason for that is Desmos has 2 different calculations. Honestly, the one that's not log mode is the better one. It only gives you the R squared value, but we want to compare these directly for that. All right, the final thing from Unit 2 that we did is the 2.2 section, which is talking about the average rate of change. And the main thing we got there was, well, we defined rates of change as change in one quantity divided by change in another quantity. You may recall the unequal pay between male and female nurses problem, and they looked at the change in percent of nurses that were male, percent of nurses that identified as male versus the percent of nurses that identified as female, and that change over time from 1940 to 1970 or something like that. And then they looked at the pay differential, which was not a rate of change. It was just the amount of money paid to women versus the amount of money paid to men. And it was like for every dollar a male earned, the female earned 83 cents or something crazy ridiculous like that, right? So that was not a rate of change. It's really these changes in quantities. Okay, so the top has a change and the bottom has a change. And then the big thing that you're going to see in the unit reviews is getting a unit rate. And that simply means a rate, so this kind of change, with a 1 in the denominator. Meaning you divide the bottom number into the top number and you get it. For example, if our rate was 3 to 4, I would divide 4 into 3, and that's equal to 0.75. So it'd be 0.75 over 1. So 0.75 units over 1 unit. It's a handy way to be able to compare things directly. And then in this section, we use dimensional analysis to convert rates into other different rates. So this is the unit, the review for the unit. This is the information I think that you should have. It always feels kind of impressive. I feel like when you look at, like if we zoom out and we look at this whole paper and you can say, wow, I learned all that. I know this. Doesn't that feel great? Also, to someone that hasn't been through the material, they look at this and they're like, what is this mess of stuff? I have no idea. And you know it. So awesome. If you have questions, please email them to me. I would love to help you. I haven't connected with many of you, unfortunately, because this is an online only class, but send me emails, show up to my office hours. I'm here to help. I'm going to make a second video talking about the exam itself. This is just the material that will be on it. I'm also going to upload this paper to JetNet, so you can look at that without just having to watch the video.